Welcome to our crash course on the Rham Cohomology and generally differential forms. So we are starting with a small, well, let's say example from either physics or like what's it called, vector calculus, if you want to put it like that. Namely, we start with an exact sequence. That you might, or that you are probably familiar with. And lastly, so we have the gradient operator taking scalar fields to vector fields. Then we have the curl taking vector fields to vector fields. And then we have the divergence taking vector fields to scalar fields. And well, what we sort of discovered, or I guess what we were told, is that on one hand, the curl of a gradient field is 0. And on the other hand, the divergence of like a curl field is 0. And that this also holds sort of the other way around. If some vector field has 0 divergence, it can be written as the curl of another field. Or if the curl of a vector field is 0, then it can be written as the gradient of a scalar field. And well, this is all very nice. It seems sort of ad hoc, and like what even are scalar and vector fields if you want to phrase them in a more differential geometric way. On one hand, and on the other hand, like this is only true for R3. Even if we go to some subset of R3, this just fails to hold. Or like some subset that is not simply connected, but this just doesn't hold. And yeah, this is sort of the one example of what we're going to talk about today, the Rham complex, because this will turn out to be just the Rham complex for R3. And I'm seeing I already have to make a short pause and connect my laptop to the power supply. Okay, so what are we actually talking about today? You may recall from differential geometry that for a manifold M, we had defined the tangent space in a point P. And now we can also take the dual vector space to that one. And we call that T star PM, just the dual space of TPM, the cotangent space. Of M in P. And similar to vector fields, a map omega from M to the union of all of them, T star PM, such that omega at point P is in T star PM, is called a covector field, or a one form, or a differential one form. Well, if we can sort of write it in local coordinates, if on a chart we can write it as some linear combination of dxi's, where importantly those coordinate functions are smooth functions. That's just some, well, technical condition in order to so that like everything we are looking at is indeed smooth. And yeah, where this is sort of the dual basis to the coordinates ddxi, which are just induced by the chart. And well, we can view those one forms as either maps. Yeah, maybe I should also mention that this thing here is written as T star M and is called the cotangent bundle. And sort of on one hand, we can see one forms as sections of the cotangent bundle, i.e. maps from M into the cotangent bundle such that at every point it is contained in the fiber over that point. On the other hand, we can also view them sort of dually to vector fields. We can sort of define, we can view them as sort of the dual space to the vector fields. We can view such a form as a C infinity M linear map from the vector fields to C infinity M. Just by defining that action at the point P to equal omega P of xp. And now based on that definition, we can just expand it to have omega take more than one argument, more or less. So this is a one form because it takes one vector field, and a k form is a, well, C infinity M multilinear asymmetric map or anti-symmetric map that takes k vector fields and produces a smooth function. Or in other words, it makes a scalar field out of k vector fields in an asymmetric or anti-symmetric way. And then we call omega km is the set of all k forms. And well, since they are maps to an R vector space, they are themselves an R vector space. And since they are like C infinity M multilinear maps to C infinity M, they also form a C infinity M module.
I understand the statement, but can you like explain it like clearly?
The last one, that it's a C infinity M module?
All the three statements, like it's the same idea, but...
Well, it's not the same idea. The fact that it's an R vector space means I can multiply them by a scalar. And that's it's a C infinity M module means that you can multiply it by a scalar field. So yeah, you can actually multiply it by a function that takes different values at different points.
I see, I see.
Yeah, and the fact that like omega as we defined it here is C infinity M linear is just because those omega p's are linear maps. And if I multiply by some function here, then this will just be SP there, which is just a real number. So then we can pull it out of omega, and then we have our linearity.
Yeah.
Okay, nice definition, but where do we actually encounter these forms? Like when I don't know, when I first learned about all of this, I was like, yeah, sure, I can picture vector fields, but what the fuck is a co-vector field? How would that be useful? And I guess I can try to convince you by providing a few examples. Yeah, so as we will also discover later, K-forms are the natural sort of chart-independent object that you can integrate. So it's sort of the generalization of line element, surface element, volume element, something like that. As an example, for one forms, if we have like a line integral over a one-dimensional submanifold in essence, written like that, for example. I mean, this is usually evaluated by saying that, okay, gamma is some curve, meaning some smooth function from the interval 0, 1 into our manifold. So then I can just rewrite it as the integral from 0 to 1 of f of gamma of t times gamma, gamma prime t dt. Where this is sort of a tangent vector. For every t. So we see that sort of the function that takes our tangent vector x to f times x, that this takes a tangent vector and produces a scalar. So R basically. So this is a case of exactly something that this is exactly a case of a one form. Because for every point, or I guess in this case then, at every t, we swallow a tangent vector and produce a number. And for two forms, I guess we can just keep on spinning this thing. So we are keeping in line with the electromagnetism. Let's now say we have a surface integral of, well, in this case, magnetic flux density along some surface sigma, where I've just said that, where I just say that sigma is like a map from some square to our surface. Then we can evaluate this thing in this way. T. So this is where this is the surface element written out for once. And we can again see that, well, this is a tangent vector, this is a tangent vector. So we're dealing with a map that maps x and y to b times x cross y. Oof. Well, and we see it is linear in the first component, linear in the second component. And because we are looking at the cross product, it's antisymmetric. So we have two vectors.
What exactly do you mean by antisymmetric?
When we exchange x and y, we get the negative.
So alternating, maybe.
Yeah,
Yes, like exterior
alternating,
algebra.
Okay.
Oh, you're already spoiling. So two, well. Yeah, there are really a lot of words for the same concept. We want to call it asymmetric or antisymmetric or alternating. Ugh.
They are not the same if your characteristic is 2.
Oh, yeah, right. Well, luckily, we are not working in characteristic 2, unless you want to define two-adic manifolds, in which case, go fuck yourself.
You're on
Okay.
YouTube, by the way, right?
I'm sorry, what?
Is it okay to cast on YouTube?
I don't know. We shall see, I guess. And lastly, if we're integrating some density over some volume parameterized by tau, where again tau is a map from some cube to our manifold, then yeah, we can write it as a triple integral, where we now have, I guess, the triple product, or put differently, just the determinant of the Jacobian, ds dt du. So yeah, this is a tangent vector, this is a tangent vector, this is a tangent vector. So we are again dealing with an alternating map that takes 3 tangent vectors and produces a real number. Okay. So now we would like to, well, firstly, we would like to know what can we actually do with those K-forms, apart from like some abstract argument that we should care about them. What can we actually do with them? And secondly, how can we even write them down? And well, I'm going to answer those questions by first telling you what we can do with them. And there are, depending on who you ask, 3 or 4 important operations on K-forms. The first operation being we can multiply them. Well, not multiplication as we are used to, but similar. So if alpha is a K-form and beta is an L form, we can define alpha wedge beta. And this is supposed to be a K plus L form. So it swallows K plus L vector fields. And what does it do? Well, the first idea we might have is that we can just plug in the first K vector fields into alpha and then the last L vector fields into beta. This turns out to be the general idea, but we have to do some more work. x l k times beta x k plus 1 x l plus k. Reason being, well, this is not alternating anymore. So what can we do? Well, we can anti-symmetrize. We can just sum over all permutations and then just apply that permutation to our indices. And well, importantly, multiply by the sign of sigma in this case. But in this case, turns out that we are overcounting a bit, so we also want to divide by some factorials just for, I guess, for nicer results. Yeah, this formula is a bit unwieldy in the end. It turns out that we will almost never use it and just use the axioms we will sort of have a look at later, just for calculations. But one example, I guess, is sort of important, namely example k equals L equals 1. Oh, by the way, what do we get for k is equal to 0 or L is equal to 0?
A scalar? I mean,
Yeah. So what do we get for the wedge product?
just the normal scalar multiplication?
Yeah, correct. Yeah, should maybe also have said that. 0 forms are just scalar fields, so C infinity M. Well, anyway, for k equals L equals 1, we have alpha wedge beta, well, eats 2 vector fields, x and y. And how does that now look like? We have alpha x, beta y, corresponding to, well, sigma equals to the identity. And then we have minus alpha y beta x corresponding to the permutation that exchanges 1 and 2. And well, in the end, we can prove that omega bullet m, which we define as just the direct sum of all of the omega k's, satisfies the axioms of an exterior algebra. And what are these axioms? Well, firstly, our wedge product is associative. Secondly, our wedge product is well, it's not really alternating or anti-symmetric, but it's, I guess you could call it supersymmetric. Well, anyway, if we exchange them, we get a factor of -1 to the k plus L, where alpha has degree k and beta has degree L. And thirdly, well, wedge is bilinear. So now we would like to, or now it would be nice to find out how we can actually write down K-forms. And well, we have already established, so writing down K-forms locally. We have already established that if we have some chart with coordinates x1 till xn, then V1 forms, or let's say omega 1 of chart U with coordinates, then we can write every one form on the open neighborhood that this chart covers. And we can write all of them down as linear combinations of the dxi. With coordinates or coefficients and C infinity U by dx1 until dxn, just because like the ddx1 and ddxn and so on, they form a basis for all of the tangent spaces, and then the dual basis is a basis for the cotangent space and so on. And well, in a similar way, we can sort of see that when we take products of these dxi, that they generate omega k. Namely, always products of k many of these. So wedge products. So then we can, because they are the dxi, they are one forms, so they always anti-commute. And this means that we can write down a local frame for omega k, so a local basis, essentially as dxi1 until dxik, where 1 smaller than or equal to I1, smaller than, and so on until ik. Yeah, and this shows a local frame of omega k. So locally, omega k is of dimension or has rank and choose k. Just because it basically boils down to the number of these index choices you can make. And well, to help with writing stuff down, because this is quite a tedious expression, we can introduce a multi-index notation. Admittedly not as sexy as for polynomials, but still. Call our multi-index I, and at every point it can take values of 0 or 1. And then we define dxi is, well, the exterior or the wedge product of, well, I guess j from 1 until n, where ij is equal to 1 of dxj. So, I don't know, for example, dx of 1, 0, 1, 0 would be equal to dx1 wedge dx3. Well, and then we can expand our form omega locally. So omega k just as a sum of some coefficients times dxi, where we define the absolute value of I, which, yeah, admittedly, I wasn't the best choice at this point, but what shall I do? Is defined as the, yeah, I guess sort of the sum of all of the components, or equivalently just the number of ones. Okay, I guess now let's go on to the second operation that we can perform on our differential forms. Because until now, I mean, okay, nice. We've basically explored that it's an exterior algebra and comes with all of the benefits of an exterior algebra over some, well, I guess some glorified vector space. And at some point I've stated that things are smooth, but like, when are we going to differentiate things? Well, now we are going to differentiate things. We can, well, we always define those operations on forms with a specific degree and then just extend by linearity, so that omega be k form, and we already write locally. Then we can define the exterior derivative of omega as, well, again, our expression. And then we add one extra index. And then we, yeah, so basically an answer to the question of, well, we want to differentiate, but in what direction? Well, in all of them. And we just sum them all up together with, well, essentially a marker in what direction we differentiated. So now we can see that those are sort of, this thing is a k form, this thing is a 1 form, and that is like a scalar function. So this thing is a k plus 1 form. And yeah, this is the expression you want to use, because the formal definition is not very pretty, but I'm still writing it down because completeness. So d omega takes k plus 1 forms, sorry, k plus 1 many vector fields, and we define this as the sum of two glorious sums. We first apply the ith vector field to omega evaluated at with all of the others except for the ith. And then take some alternating sum of that. And then we're also taking a sum over all pairs of indices, where we again have some alternation there, where we then take the Lie bracket between those two specific vector fields. And again, xi and xj are afterwards exempted. Sorry, xk plus 1.
Where did the Lie bracket show from?
Sorry, what?
Like, is this just like, why are you calling it a Lie bracket here?
Well, because it's the Lie bracket of vector fields.
Okay.
So this is, I mean, a vector field is like a derivation on the algebra of smooth on C infinity, basically. And then we can compose them because like they take scalar fields and spit out other scalar fields. And if we take sort of the difference of those two compositions, exactly like this commutator, then we again get something that's like has the Leibniz rule and everything. So it's again a differential, it's again a vector field.
No, I get that it would be a vector field, but as of now, it's just a commutator, right? Like there is no notion of a Lie bracket or.
Well,
Or
I
does
mean,
it
it satisfies the axioms of a Lie bracket, therefore
Okay.
it is a Lie bracket.
Oh, I see.
And it's also called the Lie derivative or the Lie bracket of scalar fields. So yeah, also like, sure, the vector fields on a manifold, they are a Lie algebra, but never mind, I guess. I guess we can write down one special case for this, namely k is equal to 1. Or I guess, no, let's do k is equal to 0. So we have f in C infinity m. What is df? Well, df takes one vector field. And, well, those indices go from 1 until k plus 1. Yeah, the second sum is just empty, and in the first sum we have exactly one term, namely x of f. Okay. But what I wanted to do was k is equal to 1. So we have a 1 form, and then the omega of x and y is x applied to omega y minus y applied to omega x minus omega applied to the Lie bracket of x and y. And yeah, I guess if you've noticed something in the notation, the fact that we called our basis elements dxi isn't really a coincidence. They are in fact the exterior derivative of the function xi, mapping our chart to R. I guess exterior derivative of the coordinate function. And well, again, the exterior derivative satisfies a couple of axioms, which is how essentially you are going to work with them. Axioms are, firstly, it is, well, not linear, but at least additive, or I guess are linear. If we apply it to a sum, we get the sum of the exterior derivatives. Okay, sure. Then next, if we apply it to a wedge product, well, we get some sort of Leibniz rule, or I guess some sort of product rule, but It's always called Leibniz rule. Except we have some alternating factor there, and reasoning being, yeah, basically D, you can view D as, well, one form, and if we sort of have the second expression, D has to hop over alpha, so it has to hop over a K form alpha, so you get K many minus signs. Yeah, K is the degree of alpha, very importantly. And thirdly, when we apply it twice, we get 0. And yeah, this is basically the motivation for all of those -1 factors we had in the definition, because otherwise we wouldn't get that result. Yeah, and I guess from this you can also get that it's linear. So let's calculate a few of these bad boys, I say. In coordinates. So we have, yeah, I guess I've already said it, but so if you have just a scalar function, then we can write df also as, yeah, derivative of f in the direction xi times dxi. So yeah, basically, so it's, yeah, sorry. So it's basically the expansion of a base in a basis of, or I guess we can write it as a, like as a column vector or something, namely as df dx1, blah, 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 df dxn. So meaning d acts on omega naught, I guess, like the gradient operator. Okay, now we are going to specialize to, well, let's not say necessarily R3, but an open subset of R3. And we have 3 functions, f, g, and h. And then we take the differential of the form f dx plus g dy plus h dz. And well, by additivity, this becomes that. And then we can apply the Leibniz rule. And we get a whole big expression, but yeah. H dz plus h t squared z. But now since yeah, we've already established that the exterior differential basically squares to 0, those 3 terms fall out. Then we can, yeah, then we can sort of plug in this definition, or I guess this expression for df, dg, and dh, blah, 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 well, not long calculation, but yeah, whatever. And then we get this expression. h dy minus dg dz by z plus dz minus dh x z x. And you can always see that you always have in those brackets an expression of the form ith coordinate differentiate to the jth minus our ith function differentiated with respect to the jth coordinate minus jth function differentiated with respect to the ith coordinate. Same for here, same for the third bracket. And also note that this thing is in a certain sense perpendicular to dz. This would be perpendicular to dy, sorry, x, y, z, y, z, x. And this is sort of perpendicular to dy. So this looks a lot like the curl. I guess we could write it as the curl of FGH. And I guess lastly, we can, for the same three functions, define omega. Oh, sorry, we can, yeah, define omega as df dy wedge dz plus g dz wedge dx plus h dx wedge dy. And well, if we calculate the exterior derivative of this thing, then after some calculation, we will find that it's df dx plus dg dy plus dh dz times, well, dx dy dz. So this looks now like, well, I guess you could say this thing here is sort of perpendicular to 1. So this yeah, looks like the divergence of FGH. So I guess this is a nice, I guess, intuitive explanation to what these things are. But what exactly do we mean by perpendicular? And yeah, what do and well, as always with notions like perpendicular, it has to do with the metric. So for the third operation, we actually need a metric. So if mg is Riemannian or pseudo-Riemannian, I guess.
Philip, before you start with metrics, there are a couple of conceptual issues generally have had in physics. Before we define the metric, as such, there is no unique covector for every vector. Am I correct in saying that?
That is true, yes.
So right now, all we have is like these covectors and one forms existing, and we know that the spaces are the same, the space of all vectors and the space of covectors, but there is
We
no
don't
map
know that
between
they
them.
are the same. Like they have the same dimension, sure. We can find some isomorphism, sure. But yeah, it's non-canonical.
Okay. No, I'm just
Yeah.
airing these out because these are like very confusing things to me. But okay. And so now after we would define the metric, then this map would exist.
Yes, and that is exactly what I'm doing now. I guess we can also firstly, yeah. So we introduce a metric. And the metric, well, gives us an isomorphism between Tm basically and the cotangent bundle. And this sort of plays into, I guess, note that the rank, or I guess the local rank of omega k was n choose k, which happens to be the same as n choose n minus k. But this is the rank of omega n minus k. So locally, k forms and n minus k forms are, or like locally, we could find isomorphisms non-canonically. But now, since we've sort of fixed an isomorphism of the tangent and the cotangent bundle, maybe those become canonical, or like maybe we can define some unique isomorphism between omega k and omega n minus k. And that is exactly the third operation I would like to discuss, the Hodge dual. So I'm going to again give the expression in coordinates because in this case, I don't really know a better way. So let omega be in k form. Let's say, and now I'm going to give, I guess, an expansion not in multi-indices because it's not very useful for this case. I1 until ik, dx I1, dx ik. Then we define star omega as well that same sum. And now we're also taking additional indices, namely n many. And then we have some factor of the determinant, the square root of the absolute value of the determinant of the metric.
What is
Some
n exactly? The dimension of m? N? What is m?
M is n-dimensional.
Okay.
Yeah, sorry, it's usually implied. Didn't write it down explicitly. Now we are pairing off the first k many j's. So we have I1, J1 until ik, jk. Then we take epsilon j1 until jn. And then we have the remaining j factors, jk plus 1, wedge until jn. So this epsilon is the Levi-Civita symbol, meaning the complete alternating symbol, whatever we have. Basically epsilon of 1, 2, 3, blah, 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 until n is equal to 1, and alternating. So sort of barring metric factors, what our Hodge star is doing basically is that we have some object with indices I, and then we are sort of taking the epsilon of that thing with jk plus 1 until jn. Okay, it doesn't hold up. But still, we're sort of taking the epsilon of that thing and then using the metric to raise factors, to raise indices, and really hard to explain what it does actually. So I guess let's get straight to the axioms. So it's linear, really linear, which I guess is sort of a relief. F alpha G beta. Where F and G are scalars, and those things are general differential forms. And well, since the Hodge star, oh yeah, maybe I should have mentioned that. So star omega, omega was a K form, so star omega is now an N minus K form. And well, you see, if you look at the dimensions, that if you apply star after star, you should land in omega and omega K again. Okay, bye Karthik. And yeah, it should sort of be some, I don't know, be some scalar multiple of itself again. So star of star alpha is, and now this is also a very nice expression. You have some sign factor basically. So I guess for general calculations, it would maybe useful for me to provide some examples. So we are now going to do a 3D, meaning in some open sub set of R3, we have star of 1 is equal to dx, dy, dz. What we happen to know as our volume element. Then we have dx is dy wedge dz, dy.
So the metric here is just the normal scalar product.
Metric is a scalar product valued.
In this special case, you didn't specify a metric.
Oh yeah, sorry, yes, of course. What else would I use? dz wedge dx, dz is mapped to dx wedge dy. And you can see that this is sort of the notion that I used earlier when I meant that these forms are perpendicular to dx, meaning that they are just mapped to that thing under the Hodge star. Yeah, and I guess, and star after star is just 1 in this case. So the star of dx dy dz is 1, the star of dy dz is dx, and so on. And yeah, I guess we can have some fun with that. For example, if we take the star of some wedge product, where we sum over the I and the j, it's not very hard to show that this is just the, yeah, basically the cross product of the coefficients, again turned into a K form. Yeah, and secondly, what I was already saying before, if we take the star of the exterior derivative of a 1 form, we get basically the curl of that one form, or of that thing turned into a one form. And if we take if we take a one form, turn it into a two form, like I did up, where was it? As I did here. Then apply the exterior derivative and then apply the Hodge star again. We get the divergence of that function. And yeah, I guess can also use this to express Maxwell's equations. If instead of R3 we are working in R4 and we don't use the usual scalar product but the Minkowski scalar product in 1+3 dimension, Maxwell's equations look like df is 0 and d star f is star j, where j is the differential form describing the current and f is 1/2 sum over I and j fij dx I wedge dxj, where this is just the what's it called, the electromagnetic field strength tensor. And I guess another fun thing, if we take our expressions from above, we had that star d star acts like the what was it? Star d star acts like the divergence, and so we can take, and d itself acts like the gradient, so we can take the divergence of the gradient, and I guess for good measure we can also take the dual of that. And that should be the Laplacian, and that is indeed the Laplacian. Sorry, yeah, Laplacian. I wrote Lagrangian in the lecture notes. Jesus.
Physicist.
Yeah, I mean, it's always French people who have an article in their name.
So this is Legendrian and
No, I meant Lagrangian. Generalization of Laplacian. And well, if we are acting on one forms, so sorry, if we're acting on zero forms for f in C infinity, we have star f lies in omega n. But then the exterior differential of that thing is an n+1 form, so it is 0. So then delta of f is just star d f. So the divergence of the gradient of f as was expected. And well, I guess to close this segment, this is exactly how we get these ugly expressions for the Laplacian and other coordinate systems. Yeah, I guess exercise determine the expression for the Laplacian in spherical coordinates. Or just don't. Okay, so as a bit of summary. So, Jesus, summary I can't write. if mg is a Riemannian or pseudo-Riemannian manifold of dimension d, dimension n, then the ring omega bullet M has the following structure. We have a product that is, well, not symmetric, but sort of supersymmetric. Which that adds degrees. Then we have an exterior differential. That increases degrees by 1. And we have a Hodge star T that sort of inverts degrees. Such that, yeah, this thing is, yeah, associative, supersymmetric, whatever. This thing is R linear, squares to 0, and obeys the Leibniz rule. And this thing is C infinity M linear and sort of self-inverse. And I guess we are doing a break now. So note that the idea of having a map d from omega k to omega k plus 1 with d squared is 0, that sort of rings a bell, right? I guess more to the point, we can write things in this way. So 0 forms, d to 1 forms, d to 2 forms, and so on. And yeah, so that really looks like a code chain complex. And yeah, indeed, it is a code chain complex. I guess of R vector spaces called the Rham complex. Okay, and we've sort of seen how the Rham complex then gives rise via some quotient constructions to the Rham cohomology, but I guess let's describe our actors in this play a bit more. So a K-form is called closed. If d omega is equal to 0, i.e. if omega is in the kernel of the kth exterior derivative operator, and I guess we could then also call it a K cocycle. But in this case, the terminology of closed and exact has survived. Similarly, a K-form is called exact. If omega is equal to d alpha for and alpha and omega k minus 1. Or in other words, i.e. if omega is in the image of the k minus first thing. So again, we could also call it a k coboundary. And well, since we know that d squares to 0, we know that every exact form is closed. But is the opposite also the case? And the answer is no, not generally. I guess we can take an example. And maybe Nicholas will recognize this example from EK 2. We have omega is 1 over x squared plus y squared, x dy minus y dx. If we apply the exterior derivative, well, to make a long story short, we get 1 over x squared plus y squared. This is the, one of the derivative minus x times 2x over x squared plus y squared squared. And then we have the y terms. Oh, I forgot the dx wedge dy. Well, this turns out to be 2 over x squared plus y squared minus, and then we have 2 times x squared plus y squared over x squared plus y squared squared. But these two expressions are just equal, so we get 0. Oh, I should also mention that, of course, this definition only makes sense if we exclude 0. So we have omega is closed, but not exact. That they are not exact can be seen from the fact that dx and dy are linearly independent. So yeah. So we are once again trying to measure things, as we always do in homological algebra. We define the kth homology group of the Rham complex, the kth Rham cohomology group to be of M to be kernel dk divided by the image of dk minus 1. Or alternatively, as the vector space of closed k-forms divided by the vector space of exact k-forms. Yeah, this is called the kth Rham cohomology group. Only in this case, it's not only a group, but actually an R vector space. And yeah, I guess they measure to what extent closed forms fail to be exact. But how can we tell if that is the case? And for that, we are, well, eventually trying to relate the Rham cohomology to the singular homology that we discussed in algebraic geometry, or that we discussed in the algebraic topology crash course. And to see that relation, we are first going to define our fourth and last operation on K-forms, namely integration. So, yeah, integration. Now, usually in differential geometry, you define how to integrate stuff over submanifolds. But the thing is, like you need it to be oriented, then you need an oriented atlas, and like you need a whole new way of defining your manifold even to begin with. And that's not really nice. So I'm not going to discuss integration over submanifolds. Instead, I'm going to discuss integration over chains. So, yeah, definition. Well, we are not talking about the topology stuff here. We need a bit more structure. So we have sort of have to redefine everything. So let's do that. Start with the definition of a simplex. A smooth K-simplex in M is a smooth map sigma from the K-simplex to M. Okay, what does that actually mean? I mean, this is something that has corners and boundaries and everything. So what the hell do we mean by smooth? And well, first notice that it is contained in some hyperplane of r to the k plus 1. Hyperplane. Of r to the k plus 1. So we can linearly map it to the subset of rk. And, well, closed subset. And then we can just say, well, the smooth function on this closed subset is a smooth function on a slightly larger open set that we then restrict. Well, and I guess that is everything. And then we can take linear combinations of K simplices, and they are called K chains. And now we are not going to take linear combinations over Z, but just over R. And we write C infinity K. Yeah, that's a bit unfortunate with our naming for the vector space of K chains. Just infinity for smooth, and then CKM as we are sort of used to from algebraic topology. And we again have an operator, a boundary operator from CK infinity M to CK minus 1 infinity M, where the simplex is just sent to still not sure if there should be a plus 1 here or not. I don't know. of sigma composed with the inclusion of the ith phase. And well, they form again a chain complex like the continuous version in algebraic topology. And one can in particular show that every continuous K-simplex is homotopic to a smooth K-simplex. So the chain complexes C dot infinity M and C dot M are homotopic or homotopy equivalent as chain complexes. So they in particular have the same homology. Or in other words, when we have an element of some singular homology group, we can, without loss of generality, assume it to be a smooth chain, or we can assume it to be smooth. And now we want to integrate a K form over a K chain. Definition. And how do we do that? Well, let omega be a K form and sigma be a smooth K-simplex. Define, well, the integral over sigma of omega to be, well, we originally it is just defined as the integral of the pullback of omega via sigma, but since we haven't really defined that, I guess we can give an integral expression where we integrate. Well, since we're integrating over the hyperplane, I'm just giving an explicit mapping to R to the K, namely the set where the sum of the components is less than or equal to 1. I guess if you wanted to, this is the other definition of a simplex, of the simplex, but never mind. We take omega, we plug in the k many tangent vectors of sigma, so sigma differentiated with respect to the first coordinate, the second, the third, and so on until the kth. And then we just integrate it with respect to the Lebesgue measure, the k-dimensional one. And well, we take omega at the point, now we have to do some weird coordinate transformation. I guess not that weird, but still.
Where exactly stands this 1 minus sum xi?
Yeah, okay, so we can map so the k-simplex was defined as the set of x in R to the k plus 1, where the sum, so coefficients bigger than or equal to 0, such that that sum is equal to 1. And we can map it to the set of vectors in k blah 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 xi is smaller than or equal to 1 by just mapping x0, x1 until xk to x1 until xk. And then you can just get the 0th coordinate back by taking 1 minus the sum of the remaining ones. By Nicholas.
But which one does get the 1 minus xi x1 to the xk? The one you wrote on the down right of the omega.
So that's the inverse map of that.
Yeah, I see, but where do you plug it in? Which function?
To omega.
Omega, okay.
I mean, it's always in differential geometry, it's always a bit weird, like where you put the point and where you put the vector fields or whatever you're plugging in there. So usually people compromise by putting the point just as a subscript. And that's what I'm doing here, but yeah. Okay, so this is a nice integral, I guess. Well, anyway, we can extend it linearly. To, well, we can say k chains, but we can really say that it's just a pairing of omega upstairs dot times c downstairs dot to r, where we just say if we integrate a k form over an L simplex, that's just 0 and everything else. This now has the nice notion that we can write like a composition of two paths just as the sum of the two paths, and we don't have to worry about the fact that they might be discontinuous or whatever at the point where they meet. Just don't have to care about that anymore because we can just take formal linear combinations. That's perfectly fine. And a very important theorem in that respect is the theorem of Stokes, of course, which in this language has a very nice formulation. So we have an k-1 form omega and a k chain C. Then the integral of omega over C, the integral of d omega over C is equal to the integral of omega over the boundary of C, where we don't have to worry about any kind of orientation issues or whatever, just because it's all in the definitions. And from this, we can immediately infer that if omega is closed and C a boundary, or if omega is exact and C a cycle, then this integral is 0. Just because in one case we have the integral over some boundary of a closed form, which is then equal to that integral, but omega was closed, so that is 0. Or in the other case, we have the integral of d alpha, which is equal to the integral of alpha over the boundary of C, but C was a cycle, so it has no boundary, and that is again 0. And from that, we can infer that our map integral from omega k times ck to r can actually be restricted to closed forms times cycles, and then it passes to the quotient. of the kth de Rham cohomology group and the kth singular homology group. And well, by definition, it is a linear map. Or I guess a bilinear map. Now you might ask yourself, is this map that sort of relates de Rham cohomology and singular homology of manifolds, is this like a dual pairing or something? Like, could it be that cohomology group is actually the vector space dual of the homology group? And
Indeed.
that is indeed the case, a result known as the de Rham theorem. Integral is a dual pairing, meaning that if we have this integral is 0 for all cycles, C implies omega is exact, and this 0 for all co-cycles, or for all closed forms, omega implies that C is a boundary. Or I guess, put differently, the kth de Rham cohomology group is isomorphic to the vector space dual of the kth singular homology group. And again, this is sort of the prime way how to find out if some form is exact or not. You pick some cycle, and if it turns out that the integral along that cycle is non-zero, then we know that our form can't be exact. So how exactly do we know that our form omega is equal to 1 over x squared plus y squared?
Can you maybe recall what C boundary means again? Where did you define it?
C is equal to this this partial applied to something.
Ah, okay. Thanks.
Yeah. So we have this, again, this closed form, and now we would like to actually really prove that it is not exact. And well, for that, we just have to integrate it along a cycle. Which cycle do we use? Well, I guess at this point, I've already identified the one simplex with the interval 0, 1 to R2 without 0. T maps to cosine of 2 pi t, sine of 2 pi t. Well, now is this thing closed? The sigma of this, the boundary of this is just sigma at 1 minus sigma at 0, which is the point 1, 0 minus the point 1, 0, which is 0. So yeah, sigma is closed. Sorry, sigma is a cycle. And we have the integral of omega along sigma is, yeah, I mean, it's the integral that I already calculated beforehand, or I don't know. So pullback of sigma star omega, and I guess I've already calculated in the break what this is equal to. It's equal to the integral from 0 to 1 of 2 pi dt, which is 2 pi, which is not 0, citation needed. So yeah, omega isn't exact. So yeah, another way to view this, especially in light of Stokes' theorem, is that if you want to integrate some form, and so that's really how I want to phrase this. Well, anyway, if you want to integrate some form and you can show that this form is exact, you can reduce that integral to, well, an integral over the boundary, which is smaller, so potentially less work. This means in particular that if you have a line integral and your form happens to be exact, then this line integral is just the difference of two function values. So it's in particular path independent and everything like that. And at some point in analysis 2, we had a criterion how to see if something is the gradient of something else, which was the Poincaré lemma. I get, well, Jesus, I'm rambling. What I want to say is the Rham cohomology groups measures how much the Poincaré lemma is not true, or I guess measures the obstructions to this Poincaré lemma. And we know that by de Rham's theorem, we know that these obstructions are then sort of equivalent to holes in our space, i.e. non-trivial singular homology. And I guess for the physicist in the room, I again have the two nice examples of non-trivial first and second cohomology, or dually non-trivial first and second homology. The first thing is the Aharonov-Bohm effect.
Famous example.
Sorry, what?
It's the famous example.
Of course. So we have R3 with spherical coordinates. We define B to be equal to minus bz dx wedge dy for r smaller than or equal to capital R, and 0 for r smaller than capital R. Then we know since in R3 everything, since R3 has trivial homology, we know that every closed form is exact. Okay, so bz is a constant, so the exterior derivative of that thing is just 0, which means that b is equal to the exterior derivative of some other function, or I guess some one form. For example, a is equal to minus 1/2 bz r squared d theta for less than or equal to r, or minus 1/2 squared bz capital R squared d theta for r is bigger than r. And well, this is not continuous or anything, or I guess it's continuous but not differentiable. So doing that alone was some sort of a stretch, but I guess bear with me. Because now we remove that cylinder from our space. So we consider M consists of those points in R3 where x squared plus y squared is bigger than r squared. Then we know that dA is just equal to B on that space, so it's equal to 0. But on the other hand, it's not closed. Sorry, it's closed, but it's not exact, because if you write it in Cartesian coordinates, it just turns out to be a multiple of this form we just calculated. Now you might, from a strictly classical physics standpoint, ask, why is this relevant? A is some abstraction, it doesn't occur in nature. It doesn't have any effect on classical mechanics. Yeah, true, but it does have an effect on quantum mechanics, and yeah, in a way, we can talk about some integral. I think I have that a bit later. Anyway, this shows that the equivalence class of A is non-zero. It's a non-zero element of the first Rham cohomology group, right? Yeah, because it's a one form. And then secondly, the Dirac monopole. Where we're looking at R3 without the origin, and we define again in spherical coordinates. F is equal to, well, some C times sine of theta, d theta, wedge d phi. Then df is 0, just because this coefficient only depends on theta, but when we differentiate with respect to theta, we get a d theta, which annihilates the one we have there. So it's closed. But we have, when we integrate over some sphere of some radius, we get that this is actually equal to 4 pi times c, which is not 0 in general. So f is generally not exact.
Yeah.
Yeah, and I guess the sort of important takeaway is, or I guess another observation is that if you're doing path integral physics, so when dealing with path integrals, you usually don't require that the integral, we don't want the integral, or we don't require that integral to be 0 along some closed path, but we at least want the exponential function of I times that thing to be, well, trivial, so equal to 1. So we don't need full exactness, but we need that those integrals are integers. So, and I guess for this we also need our sigma to just have integer coefficients. So this leads to some sort of, I mean, in our case here, this means that like we want this thing, I think.
I'm slightly confused by what do you exactly mean by sigma to have integer coefficients?
Sigma is a chain, so
Okay.
it's some linear combination of simplices.
Yeah.
And we want the coefficients in that linear combination to not only be real numbers, but be integers.
Okay.
That's
But there are
everything.
like factors of 2 pi that will emerge too, right? Like
Factors of 2 pi. I mean, I guess they are in the omega in this case.
okay. No, I get it.
Yeah.
Basically, this is like quantization, right? Like something like
Yes,
quantization.
yes, this is what gives us a charge quantization. In the case of the Aharonov-Bohm effect, it says that our magnetic field is somehow quantized, so it can only take discrete values. And yeah, for Aharonov-Bohm and for the Dirac thing, we have 4 pi times c, which is supposed to be an integer. At least I think that was, well, anyway, we get some form of quantization for the charges, which is in itself a non-trivial thing. And I guess that was all I had to say.